A recent 2022 paper, published in the journal Nature, found something interesting. When human brain patterns were measured in experiments and compared to AI language models, there were some uncanny similarities. Particularly in the way both systems process language, specifically in the way that they predict words from context. In addition to this, their neural activations mirror each other. The AI's internal activities, quote, significantly map onto human brain responses to written sentences. So it sounds weird, but according to this research, we're beginning to learn that AI language models are behaving like human brains. Kind of surprising, but maybe it's just the fact that technology is starting to help us understand biology. So back to the robot. In summary, the physical robot acts as the language model's hands and eyes, while the language model supplies the knowledge about the task at hand. To give an example, a user can ask a task, "I've spilt my drink." The robot interprets the sentence using the language model. It comes up with a bunch of solutions in its software, but only selects what it's capable and best at doing. It then analyzes its environment to see how to physically proceed. Okay, so what? This couldn't have been that hard to do, right? Well, there's a lot of careful engineering that had to be done to make this possible. If you ask an AI language model a question, it will give you a sensible and reasonable answer, but that answer may not be feasible or useful to the robot. For example, if you say, "I've spilt my drink," the language model may tell you, "You could try using a mop," but if there is no mop in the scene, or if the robot is incapable of using a mop, the task is impossible. Google researchers managed to create a way for the robot to understand what it can and can't do, but more on this later. AI computer vision was used to pair what the robot is seeing with its vast knowledge base from the internet. The robot can understand and complete a task as complex as, "I spilled my orange soda, can you throw it away, bring me something to help clean it up, and then bring me a replacement?" So in all of this, the key here is that the machine ends up being pretty open-ended. It's general. Industrial machines, for example, have to be precisely programmed to do a very specific task. So how is understanding achieved? Google Research is using their PaLM model in the robot. So what on earth is PaLM? PaLM stands for Pathways Language Model. It's an algorithm that's been trained on countless amounts of text from the internet. We're talking hundreds of billions of parameters and petabytes of text. The result of all of this training is its ability to understand language. It's important to note that these types of massive language learning models are pretty new, only around 2 years old. The vast levels of training on billions of parameters makes them vastly different to services like Siri or Alexa. In addition to the PaLM model, the researchers used another system of code to let the robot know what it can and can't do. This code, called world grounding, trims out unsafe or nonsense actions.
Machine learning is one of the few things that we have that really makes it possible to get computers to behave intelligently in unstructured environments. By using experience, using data, using things that the computer has seen in the past to figure out patterns.
Reinforcement learning is one of our big bets. It's a machine learning algorithm where each time the robot attempts to do a task, we can reward it if it succeeds, tell it that it didn't succeed if it fails, and then the things that lead it to succeed get rewarded more and more often, and it gets better and better at the task. And this is something we can do across many robots at the same time to share that learning and that experience.
To speed up the learning process, the software was trained in a virtual world so it could gain the benefits of knowledge through a simulated environment, but without having to spend mass amounts of time in the physical world.
We can really multiply our impact by having the robots also practice how to do things in simulation. We can do things like simulate many other buildings and many other types of objects and many other types of lighting conditions and backgrounds.
And what we've been able to do with the simulator is significantly reduce the amount of real-world data that we've needed, on the order of going from about 500,000 attempts all the way down to only needing 5,000 attempts to learn grasping.
We've seen this method before in the episode about OpenAI and their dexterous hand robot. I thought it was a very clever idea then. So finally, the robot's world grounding was tied into another section of code that turns high-level instructions into low-level subtasks that can then be performed. Once all of this is done, you have a robot that can understand and then perform tasks without human intervention, and it does so better than anything else out there at the moment. In their paper, Google claims that the language model and robot selects the right sequence of skills 84% of the time and executes them successfully 74% of the time. This is a 50% improvement over the previous latest research. The computer scientists also state that the performance keeps improving when the language model does, so this could get much better pretty quickly. The team stated that the mobile robot could accomplish a large set of abstract instructions in a real kitchen with objects it's never seen before. The significance here is that this is the first time a large-scale model has been used in a real-world robot. It can be seen as a hallmark in the field of robotics. These findings suggest that the field of robotics can benefit from the improvements in language modeling. This could bring the two areas of research closer together in the future. As for the robots, 100 of them are doing autonomous tasks around Google's offices.
It has to wander around buildings, find the trash cans, look in them, understand what's in them, and if something's in the wrong bucket, look in those buckets, robot, and if you can, move it into the right bucket.
The sorting experiment is really pushing us to try and write an application that improves by itself, just through practice. Is that gonna work? I hope so. The way we made it, the tools and recipes we used to create this pick an object out of a bin capability, we'll be able to use that same recipe to learn a new skill.
The more we give the robots a problem and they get better at it just by trying to get better at it, that's the thing that will convince us that these robots are now ready to go solve lots of problems for people in their everyday lives.
So that was kind of a lot to get your head around. But what does this mean for the future of robotics? Although it is a major milestone, right now, Google's robot is pretty slow at completing tasks and can only grab basic objects. But then we have to ask, what about in 15 to 20 years? Will we have to worry about physical automation for entry-level jobs like fast food? Taking into account the current pace of advancements in both robotics and the new AI that's starting to power them, this could be a strong possibility. But on the flip side, there are plenty of other use cases too. Language model robots could be useful in anything from aged care to growing food or cleaning up dangerous waste and pollution. Robots like Spot have already proven the latter possible. In any case, the future is definitely going to be interesting. As for me, in summary, I wouldn't exactly want one of these Google robots in my house, but I definitely do see the value in the research for certain situations.